Hi everybody. In this video we're going to start off chapter 3, which is called probability. And now this is going to be a little bit of a change of pace from what we've done in the first two chapters. In chapter 1 we've defined did a lot of definitions and looked at an overview of some of the stuff that we're going to talk about, but a lot of definitions. Chapter 2 was all about describing data, and we're taking a turn in chapter 3 because there's going to not be the same type of data per se that we were working with before. We're taking the stuff that we did before was very concrete and very descriptive. But now we're going to move on into a sort of theoretical world of probability and what probability is and why it's going to be important for this class. And so chapters 1 and 2 are very descriptive, very concrete examples and things you're okay with, or hopefully you're okay with. Chapter 3 and chapter 4, which we'll get to eventually, are a little bit of a change into what we're going to see more in the later part of the course. This is a sort of a bridge between what we've done and what we're going to do. So anyway, just keep that in mind as we go forward. So section 3.1 is about defining probability. And so probability is something that you probably, you've definitely heard the word before, and you might even use it, but you probably haven't defined it before. And so that's going to be new and interesting. So probability is extremely important to understand when you learn statistics because it's the basis upon which all statistical methods were built, meaning it's really important and it's going to be present in everything that we do. And it sort of sets apart one of the reasons that it sets apart mathematics and statistics, is this idea of probability and how we're going to use probability. We're going to use probability to build tools and describe and understand apparent randomness. Okay. Probability is often framed in terms of a random process which gives rise to an outcome. So what I mean by that is if you have a dice, a six-sided die, and you roll that die, the process of rolling a die is random because you don't know what it's going to be before you roll it. Okay? So it's not predetermined before you roll the die what the outcome is going to be. The same way with flipping a coin. So the things on the left of the little diagram that just popped up here, the things on the left are called the random processes. So, and we're going to look at common ones: rolling a die, flipping a coin, doing various things, looking at playing cards, so on and so forth. But it can be applied to a lot of things in life in which you don't know the outcome before it happens. And so the action is the random process, and then the outcome is what you see when the random process happens. So when you roll a die, a six-sided die, a usual six-sided die, you have 6 possible outcomes: 1, 2, 3, 4, 5, or 6. And when you flip a coin, you have heads or tails. And so that's the way in which we sort of define probability. And to make this, I guess, even more confusing, there are many definitions of probability, and we're going to use the one that we can sort of wrap our head around. There are more complicated ones as well, but probability for us is going to be the proportion of times that the outcome would occur if we observed the random process an infinite number of times. So if I asked you, for instance, what's the probability of flipping a coin and it coming up heads? I think everyone would agree that it was 50%. But how do we really know it's 50%? And that's the sort of question that we're going to think about here. How do we know that it's 50%? Well, by this definition, it's if we flipped that coin an infinite number of times for our entire life and everyone's entire life. They just flip this coin many, many times. then half of those times that I flipped the coin, it would land heads, and half it would land tails. Or that's hopefully what we would find when we do the flipping. Okay, so there are again some terms as usual. When we define a new concept, we need to look at the terms. And so there are a few terms here that are going to be sort of weird to think about, but we're going to do a number of examples. The first term when talking about probability that we need to think about is the sample space, and it's the set of all possible outcomes of a random phenomena, or that random process that I talked about before. Sometimes I'll call it a phenomena, sometimes I'll call it a process. Okay, and so the random phenomena or the random process might be sort of multiple random processes together, we'd say. So it could be not just flipping a coin once, but it could be flipping a coin twice. And so if I flip a coin twice and look at each outcome, then then if you think of all the possibilities that could happen, it's no longer just heads and tails, or heads or tails. So if I flip a coin twice, there are actually 4 possible outcomes. I could get heads both times, I could get tails both times, and then I could get one of the combinations of heads and tails. And so there are the 4. The sample space is that the 4 things that I have in the parentheses to the right of flipping a coin. So if I'd ask for a sample space of flipping a coin twice, you would give me heads, heads, tails, tails, heads, tails, tails, heads, like we have over on the right. Okay, so the sample space is the set of all possible outcomes. An event is a subset of the sample space, and it usually corresponds to a particular outcome or a group of outcomes. So, for instance, I could have an event A, and my event is described at having at least one head in the 2 flips from up above. And so the event A, if I said at least one head in those 2 flips, you would say, well, what encompasses at least one head? Well, both heads, and then one head, the head on the first flip and the head on the second flip. So 3 out of those 4 events, 3 out of the 4 events in the sample space were event A. Okay, and then I made up another event B, both tails, and that would be the 4th one. But I just made them up at random, event A and event B. It's not always going to be the case that the 4 of them are like cut up into 2 different events like they are here. Okay, so with the sample space and an event, we can then again sort of define probability here. So the probability of an event happening, okay, is going to be the following. And it's the following only when all outcomes are equally likely. So that part right there is really important. When all of the outcomes are equally likely, the probability of an event is going to be this. Okay? Which is a formula. It's got some things in it. Okay? It has some functions. So this is an idea if you've been in algebra before, which is assumed that you all have, but it might have been a while. Okay, I have a letter, so I have 3 functions here. A function is where you plug something in to it, and it gives you something out of it. And it's written like the function name first. So the P and the C here are functions. And then what I plug into the function goes inside of the parentheses. So I would read this. So I would say like the probability of A, or P of A, is equal to this interesting C function. Now, C stands for something called cardinality, but we aren't going to use those fancy terms here. Okay, the C function counts the number of outcomes in the event or set. Okay, and so my probability is defined as the number of outcomes in the event divided by the number of outcomes in the entire sample space. Okay, so if I go back here, and if I ask the question, what's the probability that out of 2 coin flips I get at least 1 head? So event A that I've defined up above, what's the probability of event A? Okay, you would say how many outcomes are in event A, so you count them. I'm sorry, you count them. There are 3 of them. Okay, how many outcomes are in the sample space? 4. And so the probability for event A, the probability of event A happening is 3 divided by 4, or 75%. Similarly, with event B that I've defined here, there is 1 outcome in event B and 4 outcomes in the sample space, and so the probability of event B happening is 1 divided by 4. Does that make sense? Well, let's check. So I have a your turn here. Okay. Suppose that my random phenomena is that I roll 2 fair 6-sided die. So I have two die. Each of them is labeled 1 through 6. Okay. Think of them as red and green if you want. You can give the die different colors. Excuse me. You can give the die different colors, okay, and then you roll them. And I want you to do the following. I want you to write out the sample space, okay? The hint is that there are 36 outcomes in the sample space. So it's a little bit of a large sample space, okay? But I want you to write them out. 36, there's going to be 36 of them, but write out the sample space. Write out the event that the sum of the dice is at least 7. So I want you to count how many outcomes of those 2 die rolls that you did that are at least the sum of the 2 numbers is at least 7, and then find the probability, which is just combining the second and first parts. Okay, so I'll stop. I'll pause for a second to give you a chance to do this. Your turn. Okay, we're going to move on to thinking about events, more than one event, and how you work with them. So there are special, or rather, there are going to be special properties about probability that we need to keep in mind, or that we'll see a lot. So when I talk about 2 events together, they can have a number of properties. And one of them is that 2 events can be disjoint or what's called mutually exclusive. So those 2 terms, disjoint and mutually exclusive, they are the same. They mean the same thing. And events are disjoint or mutually exclusive happen when, or they are described as 2 events that cannot physically happen at the same time. Right? They share no common outcomes. So no outcome is in both A and B. And if 2 events are disjoint or mutually exclusive, so they share no common outcomes, they can't happen at the same time, okay, then you get a number of rules based on that. And so one is the addition rule of disjoint outcomes. Okay, if A1 and A2 represent disjoint outcomes, then the probability that one of them occurs, that A1 or A2B occur, is A1 plus A2, which is nice. It sort of seems like it should work that way. Okay, and then if you have more than 2 outcomes or events, you can add them. So just like you did with the top part, you can add more than one. That's what the bottom is saying. Okay, and so I have another your turn, and this is where I'm going to end the video, is that I want you to complete this your turn. Okay, there's a database or a data set from our book about loans, and we've looked at those loans from a Lending Club platform. One of the variables is home ownership. Of the 10,000 borrowers, 3,858 rented, 4,789 had a mortgage, and 1,353 have owned a home. Okay? And so then I want you to ask yourself a number of questions and answer them. One, are the outcomes disjoint? Two, so the outcomes of home ownership, of the home ownership variable disjoint. Does that mean, can they happen at the same time? Do they share common outcomes? Or do they share common values? To determine the proportion of loans with the value mortgage and own separately. Okay, so proportion of loans with the value mortgage, find that, and then the value own separately. Okay, and then in step 3, I want you to use the addition rule to compute the probability that a randomly selected person from the data set, or randomly selected loan from the data set, is for someone who had a mortgage or owns a home. Use that addition rule that I just talked about previously to answer that question. Okay, we'll go over this in class on Monday.